Hello, so this is video number 2 of section 4.7. So this video, actually, we're just going to do 3 examples and then we will be done with the section. So I'm going to do this a little out of order of how it appears on the sheet. So example 1 is a little shorter than example 2, and so I wanted to just get started right away with example 2. This will sort of be our main topic. This example here will be our main topic of the video, but I'll go over 2 more. And so with this question, there are actually 2 specific questions in it. And so I'm going to do the first one, and I'll leave the second one for the viewers at home. So this question, we're given 2 bases, B and C, for R2. And so notice this, we're now sort of going to go back to restricting ourselves to R2, because what we're given now are 2 basis vectors, B1 and B2, C1 and C2, and we want to find the 2 change of coordinates matrices from B to C and C to B. So if you'll remember from, so we're going to start off with P from B to C. So if you'll remember from last video, this matrix is the 2 by 2 matrix whose columns are, and so this is the solution here. I'll draw a dotted line. This is the matrix whose columns are the B1 and B2 representations of B1 and B2 representations under the basis C. So last video we had these, right? So sort of the big thing last video was that we were given, we were given the B1 and B2 representations under the basis C. So in terms of these C1 and C2 vectors, here we don't have them. But since we're in R2, we actually have a way to solve for them. And so notice what we want to do is solve the following 2 matrix equations. Where here, the columns of the matrix are the C vectors, right? And the solution vectors are the B vectors, right? And so notice here, this will be the B1. So this solution vector here, x1, x2, will be B1 sub C. This vector will be B2 sub C. And this is because, again, we're solving for the B1 and B2 representations of under the basis C. So if I can find these 2 vectors, which give solutions to these 2 matrix equations, I'll find these 2 vectors, which will give me P from B to C. But notice the way I would solve both of these matrix equations is to augment, right, this 2 by 2 matrix by that vector, do a set of row operations, and decide what I get at the end. But notice the set of row operations I would do would be completely defined by the first 2 columns, right? So no matter how I augment this third row, and you might remember this sort of from how we solved homogeneous equations, no matter how I augmented this third column, I would do the same set of row operations because the pivots would go in these first 2 columns. So in solving each of these matrix equations, I'd set up an augmented matrix, do the exact same step of row reduction steps, and get 2 solutions in these 2. But if I'm going to do the exact same step of row reduction steps, I may as well just augment this matrix with both vectors at once. And so notice what I'm doing here is setting up the matrix whose columns are C1, C2, B1, B2. And what I'm going to do is I'm going to row reduce this matrix so I get the identity on the left. What I'll get on the right are the two column vectors giving me solutions to these two equations, which will then give me these two vectors here. So we're going to do some row reduction. Make sure I got the correct. Yep. So this matrix here is actually just P sub B to C. And so I'll write this out sort of in detail exactly why this is the case. But so the matrix I get here is the matrix I'm looking for. And notice this is because, again, we've solved, so this is B1 sub C, this is B2 sub C. And remember, all we did was we just solved for this vector in terms of these two vectors. And so we can do a quick check here to make sure that our work was correct. So it should be then that -7, 5 is equal to -3 times 1, -5, plus -5 times -2, 2. Well, so this is -3 plus 10 is 7. This is 15. Minus 10 is 5. And so then we should get the same thing with B2, except with the second column. And sure enough, 1 plus -4 is -3. -5 plus 4 is -1. So again, what we're solving for in this matrix are the two columns giving me the coordinates needed to represent B1 and B2 in terms of C1 and C2. All right, so we checked our solution for this matrix is correct. Now, we could do the same set of steps to find, right, P from C to B, right? And so we know that this matrix is going to be basically just everything done in the opposite direction. So this is going to be the C1 and C2 representations under my B basis. But if you'll remember from our last video, we know that in fact these two matrices are inverses of each other. And so we know that the second matrix that I need to find is actually just the inverse of the first. Well, the determinant of this matrix is equal to -6 plus 5, so its determinant is non-zero and it is invertible. And so calculating the inverse of this matrix, I get that P from C to B. Well, so the determinant of this, like I said, is -6 plus 5, so it's -1. And so this should be -2, 1, -5, 3. And so thankfully calculating the second of these matrices is a little quicker than calculating the first, but that gives us both of these matrices. And again, we can check our work here to make sure this is correct. So this time around, I know that this should be the C1 representation of, and maybe I'll just do one vector here. So this should tell me that C1 is equal to -2 times B1 plus 1 times B2. Or sorry, -5 times B2. All right. Well, -14 plus 15, good there. -10 plus 5, we're good there. And so you could check now to make sure C2 is equal to 1 times B1 plus 3 times B2. So what's nice about these, again, there's sort of a nice built-in way to check, is our solution correct, like so. And because these matrices have the nice relation of being inverses, we really only have to do half the work, right? So to find this matrix, it was a little bit of work, a little bit of row reducing, but once we get one of these 2x2 matrices, the other can just be found by taking an inverse. All right, so like I said, there is another example just like this on your worksheet. I would highly recommend working through it. It'll be, again, sort of this exact same problem I just erased on the board, but with different numbers. So you can try going through the same steps again. So the first example. So this one basically just sort of confirms that that what we've kind of already learned about change of coordinates matrices works under all of this new definition. And so notice if I have now one basis for Rn and the standard basis for Rn. Right, so here B is some basis for Rn. This is the standard basis for Rn. Remember where this is the vectors 1, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0. As we've already seen, so notice this is equal to B1 under the standard basis representation all the way out through Bn under the standard basis representation. And so if we're going this way, the change of coordinates matrix from B to the standard basis in Rn, well, notice that the basis representation of any vector x under the standard basis is just that same vector x. And so this is just the matrix whose columns are given by these basis vectors. And so we've actually already learned this. I think the book includes it, and I think it's good to be included just to sort of confirm that this previous definition, which we had introduced before, still works with the some of the new terminology we've built up. And so notice here, again, if we're going from B to the standard basis, then the change of coordinates matrix is just the vector whose columns are given by the basis itself. And remember, this is because, right, so this matrix here should satisfy that any vector x, right, I can get the actual vector x by multiplying p from B to E times the B representation of x, right? And that's because we'd say that x is equal to y1 b1 plus yn bn, where x sub b is equal to y1 through yn. And so you can see here that then this matrix multiplication would hold up correctly. And so in fact, this is a little odd, but you can actually sort of now think of like this, when we define just a standard vector x like this, you can think of like, you know, in a weird way, you can think of like these two vectors as being kind of one and the same vector. You know, if I have a standard basis and a other basis b, right, basically just two different ways of expressing the same vector, because this is just, right, the standard basis representation of x. And this is just the b representation of x. So in a way, like, these two vectors are kind of the same vector. All we're doing is just sort of changing the way we encode how we're representing those vectors. And so, especially now that we sort of looked at this idea of dimension, and like, we can actually sort of, vector spaces are kind of in a way defined by what bases we choose to use to define them, right? So like, again, these two vectors are the same, it's just which bases are we using to represent that vector. And of course, they're not exactly the same, right? Because they would have different entries, but you can kind of think of them as representing the same vector in that sort of a way. And so in that way, you can think of a matrix as also sort of as this tool that you could use to change the basis representation of a set of vectors, right? Especially a square matrix in that way. So like I said, a little weird, and it sometimes gets bogged down in really weird notation, but it's actually really cool, I think. Like, this sort of idea that, like, these two vectors, even though they're not equal, if we look at them under the right matrix, sort of under the right change of basis matrix, they're kind of representing the same vector. So anyways, I want to finish up with one more non-Rn example. So we'll look at sort of an example of what we can do with this in our next favorite vector space, which is the set of polynomials of degree at most 2. So we're going to say in P2, we want to find the change of coordinates matrix from this basis b, which will be 1 minus 3t squared, 2 plus t minus 5t squared, and 1 plus 2t. I always joke that you can sometimes pinpoint a mathematician by how they write their t's, because we have to make sure that t's don't get written the same way as plus signs. So we want to convert this from b to the standard basis, which for P2 we considered the standard basis to be the set t squared t1. And then we want to write the polynomial p of t is equal to t squared as a linear combination of elements in B. So we want to do two things. We want to find, and for now I'll just call this change of basis matrix P. Well, I guess we can name the standard basis here, we can name it E. And so we want to find the change of basis matrix from B to E. And then we want to express t squared as a linear combination of elements from B. So because we've already seen this nice relationship between the set of polynomials of degree at most 2 and R3, right, we can actually, again, just very carefully, we'll let the first row represent our t squared entry, second row represent our t entry, and the third row represent our constant entry. Notice we can express each of these basis vectors as a column in this change of basis matrix. Right, so this is the column vector representing my first basis vector, the column vector representing my second basis vector, and the column vector representing my third basis vector. And as we've learned, this is just the change of basis matrix from non-standard basis B to standard basis E. And so if we want to write P sub t in terms of the standard basis B, we want to solve the following matrix equation. Right, because notice this vector is going to be the B representation of P of t. Right, so here I've got the standard basis representation of P of t. This is the B representation of P of t, which we want to solve for, and we know that this matrix times this vector should give me the standard representation of P of t. And so this turns out to just be row reducing an augmented matrix. And so doing some row reduction steps, I got the following row reduced matrix of 1, 0, 0, 3, 0, 1, 0, 2, negative 2, excuse me, 0, 0, 1, 1. And so this means that C1, C2, and C3 are equal to 3, negative 2, 1. And of course we could check this. You'd want to make sure 3 times this polynomial minus 2 times this polynomial plus 1 times this polynomial is equal to t squared. And so again, by using sort of this idea of being able to correspond these polynomials to vectors in R2, we can also do problems like this when looking at non-standard vector spaces. So that actually will wrap up this section 4.7. And so we're actually done with chapter 4 now. So tomorrow we will start chapter 5.1, or just chapter 5, I guess, section 5.1, which is eigenvalues, which is, I think, maybe the coolest part of linear algebra.